So welcome to Chapter 2 review about periodic table, elements, the atom, and the mole. Here we go. So in the periodic table we talk about elements, and elements have symbols. The symbols start with a capital letter to start new elements. So for instance, here we have calcium and chlorine. Subscripts tell how many atoms there are per molecule. So if you have a subscript 2, that's 2 of whatever the element is before it. Okay, now we need to remember about the atom makeup, what makes up an atom. First we're going to talk about a proton. They are found in the nucleus. They have a positive 1 charge, and it weighs about 1 AMU. Next up is the neutron. It's found in the nucleus. It has no charge, and it weighs about 1 AMU. Finally, we'll talk about the electron. An electron orbits the nucleus. It has a -1 charge, and it weighs about 1/2000th of an AMU, or the lightest unit. So here we have the proton, neutron, and electron. You need to be able to tell about them. Now we also use these in making up nuclear symbols. Now also remember, when you look at the particles, that the electron is the smallest particle. And that goes with it weighing 1/2000th of the other two. So these two are what makes up your mass number, or your weight of each of the different isotopes. And we'll talk about that in the next slide. Okay, so now we're going to talk about isotopes and nuclear symbols. Say we had the isotope mercury 202. This number is the mass number, and the mass number is equal to the number of protons plus the number of neutrons. Now to write the nuclear symbol for mercury, mercury is H, capital H, small g. We're going to take that mass number, and that's going to be written on top, 202. And on the bottom, we're going to write the atomic number, which for mercury is 80 from the periodic table. Now, to find the number of protons is going to be equal to the number of electrons in an atom. So whenever you see atom, that means neutral. So if it's neutral, you have the same number of protons as electrons. And the number of protons is equal to the atomic number. So here we have 80, and that is the atomic number, and so that's equal to the number of protons and equal to the number of electrons. Now, the 202 is the mass number, and the mass number is, again, the protons plus the neutrons. So if I want to find the number of neutrons, then I take the mass number and I subtract the number of protons, and that will give me the number of neutrons. So here I'm going to take 202 minus 80, and I get 122, and that is my number of neutrons. And you need to be able to do this for any symbol that you're given. Now, they might give it to you like it is right here, or they might just say HG-202. Same thing. When they give you a number, they're giving you the mass number. Okay, so isotopes have the same number of protons, which is the atomic number, and that identifies the element. So it's the same element that you have every time with isotopes. What is changing is the number of neutrons. You have different number of neutrons. And because you have different number of neutrons, you have different mass numbers, because the mass numbers are equal to the protons and plus the neutrons. And that's what's changing in isotopes, are the neutrons, the number of neutrons. You have different number of neutrons. So that's the big change. Now the lithium, if I take any isotope, it can be given to me any couple different ways. It can be written like this, lithium-7 or Li-7, or it can be written as Li with the 7 up above. Now, a nuclear symbol has the mass number on top and the atomic number on the bottom. Now, a lot of times they leave off the atomic number because you can get it from the periodic table, and then they have the symbol. So, if I wanted the full nuclear symbol for lithium, I would write 7, 3, Li, like that. So all I have to do to find the number of neutrons is just take the top number minus the bottom number, and I've got 4 neutrons. The bottom number tells me the number of electrons and protons in a neutral atom. So I would have 3 protons and 3 electrons. So I can really quickly see that. Now I might have lithium 8 or lithium 9. It's still 3 for the bottom number. The only thing that's changing is the top number, and that changes my number of neutrons. Okay, so you need to be able to, given data, find out, using the percent of each isotope, how to get a mass on the periodic table, or how to compare it to a mass on the periodic table. So I'm just going to put some bogus data here, and say that I had, lithium-7 and I had lithium-5, and I don't even know if they really do exist. But I do know on the periodic table that the mass of lithium is 6.941. Now, the question could be something like, which isotope of lithium is in greater percent? Is it lithium-5 or lithium-7? Well, looking at the number here, this is closer to 7, right? A lot closer to 7 than it is to 5. So I must have more of the lithium-7 and less of the lithium-5. So I would report that lithium-7 is more abundant. Now, we're also going to have questions in which you're going to be given the percent for each of the isotopes. So say that, and I'm just going to make up a bogus element here. We'll call it BG for bogus. And I had bogus element here of 8. And of 8, there are 30.16%. And I have bogus here of 11. And it's a percent of 40.25%, and I have a bogus of 14, which is made up of 29.59% of the whole amount. Now, if you remember, all I have to do to get the final mass that would be up on the periodic table is take and times these like this, and then add them up. So let's do that. And I get 1098.29. Well, that couldn't be it, but notice I left it in percent. So I've got to get it out of percent by dividing by 100, and doing that, I end up with 10.9829 from my calculator. Now, I only have 3 significant figures because the 8, 11, and 14 are exact numbers, so I would report 10.983. Now, I can tell that this is a good number because it is between 8 and 11. If it's not between the isotope numbers, it's outside of that range, then I know that's not a right number and I've done something wrong. So you should be able to do this calculation like I've done and get an answer to be able to report. Now we come to the part where we're reviewing Avogadro's number in the mole. Remember that Avogadro's number is 6.022 times 10 to the 23rd. And that's atoms if it's an element. It is molecules if it is a compound. And if it's part of an element like an electron or a proton or a neutron, then we call those particles. Okay, and we get that. Now, this all is equal to a mole. Okay, so a mole is like, remember, a mole is like a dozen. It's a chemist's dozen, only we have a lot more than 12 in our dozen. 6.02 times 10 to the 23rd. Now you need to be able to go back and forth. So you need to be able to say, okay, if I have 0.5 moles of hydrogen H2SO4, sulfuric acid, let's do that one. Then I have 0.5 times 2, which is 1 mole of hydrogen, to every, the 0.5 times the 1 on the sulfur, 0.5 moles of sulfur, to 0.5 times 4, which is 2 moles of oxygen. Now each of these are equal to 0.5 moles of H2SO4. So I can set up conversion factors or fractions using any one of these three equalities to convert back and forth between anything that I want to from a molecule to an atom. Okay, so dimensional analysis. We're going to need the mole map, and we're going to be working with mole stuff, going back and forth with that. So say that I had 15.3 grams of sodium chloride. And I want to find out how many atoms of sodium are in there. Well, the first thing I want to do is I want to take up sodium and chlorine, and I want to look up the mass on the periodic table. Now sodium is 22.989, I think, and chlorine is 35.453. Now if I'm off by a little bit, I'm just doing that from memory. We're going to add those together. Okay, and we get 58.442 grams, and that's how many grams are in 1 mole of NaCl. Okay, so now I'm going to start with what I was given, which was the 15.3 grams of NaCl. I'm going to start a factor label so I can keep track of my units, and I'm going to get rid of the grams, so I'm going to want to put that on the bottom. So I put the 58.442 grams of NaCl on the bottom, and on the top I'm going to put 1 mole of NaCl. Now at this point I can cross out my grams of NaCl, and I can go to the next state. Since I want atoms of Na, and I've got moles of NaCl, I can say, okay, well, in 1 mole of NaCl, there is 1 mole of sodium. And I can use that conversion to set up the next fraction. I want to get rid of moles of NaCl, so it's going to go on the bottom, 1 mole NaCl, and on the top I'm going to put 1 mole of sodium. Now is it always going to be 1? No, it just happened to work this way in this time. So we can cross out moles of NaCl, and now we can take and get our answer by multiplying through the top and dividing by the bottom. Since there's only one number on top and bottom that isn't a 1, we can do that really quickly by taking 15.3 divided by 58.442, and we get 0.26. We have 3 significant figures, so 2, and that is moles of sodium. And that's what I would report for this answer. They'll also have you do just some simple ones where you just are given that you have maybe of C6H12O6, maybe you have a 0.25 moles of this. And they want to find out how many atoms of oxygen. I better put oxygen because it looks like a 0. Okay, so starting again, start with 0.25 moles of C6H12O6, and we can convert. We can put 1 mole of C6H12O6 on the bottom, and for every 1 mole of that, I get 6 moles of oxygen. So I can put the 6 moles of oxygen on the top. Now, if I go ahead and cancel that out, I'm not quite to atoms, right? So I need to add one more conversion. In every 1 mole of anything, right, and it can be oxygen, there are 6.022 times 10 to the 23rd atoms of oxygen. And now we can cancel out moles of oxygen, and we're in what we want to be as far as units. So we're going to take and times that through. We've got ones on the bottom, so all we have to do is times through the top. Okay, we have 2 significant figures, so we're going to report 9.0 times 10 to the 23rd. Make sure you're looking for that E number on your calculator, because that's the 10 to the times 10 to the power. And the units are atoms of oxygen. So this is our answer. Okay, so say that I had this again, 0.25 grams of C6H12O6, and I wanted to find out how many grams of this was carbon. So, first thing I'm going to need to do is add up the molecular mass of the C6H12O6. So remember, carbon is 12.011, and I need 6 of them. And hydrogen is 1.0079, and I have 12 of them. And oxygen is 15.999, and I have 6 of them. I'm going to add those together. Okay, this adds up to 180.10. That'll give us 5 sig figs, much more than we need, grams in 1 mole. Okay, so we're going to take and set up a factor label of 0.25 grams of C6H12O6. And we're first going to convert out of grams into moles. So in 1 mole, which is what we want to get to on the top, of C6H12O6, there are 180.10 grams of C6H12O6. So at this point I can cancel out the grams of C6H12O6. Now I'm into moles. Now I can say, okay, well, in 1 mole of C6H12O6, H didn't want to fix, there are how many carbons? Well, there's 6, so that means there's 6 moles of carbon. So at this point, I can go ahead and cancel out moles of C6H12O6. Now I'm in moles of carbon. The last conversion is to get it into grams of carbon. So in 1 mole of carbon, there's 12.011 grams of carbon. And again, I can cancel out moles of carbon with moles of carbon. Now I'm going to take and I'm going to times to the top and divide by the bottom. There's only one number that isn't a 1 on the bottom, so I don't need to worry about parentheses. But if I had something that had more than one number on the bottom, make sure you use parentheses when you divide. Okay, so I plug that through my calculator. We've got 2 significant figures, and I end up that I get 0.10 grams of carbon. Now, it's got to make sense. It can't be more than the 0.25, which it's not. So this does make sense that it could be 0.1 of it be carbon. So make sure your answers make sense when you get to the end. Okay, you also need to be thinking about it in words. So if I have 1 Avogadro's number, that's equal to 1 mole. So if I have H3PO4, then if I have 1 Avogadro's number of this, then I have 1 mole. So you'd also have 3 Avogadro's numbers of hydrogens, which would be equal to 3 moles of hydrogen, which would be equal to 3 times the atomic mass of hydrogen. We'd also have 1 Avogadro's number of phosphorus, which is 1 mole of phosphorus at 30.974. So 4 Avogadro's numbers of oxygen is equal to 4 moles of oxygen, which is 4 times the mass of oxygen of 15.999. Now we can take that and we can all add that up, and we get the total. So in words now, we've got 1 Avogadro's number of H3PO4 is equal to 1 mole of H3PO4, which equals this mass right here. So we can break it down into parts, and they can do it in words or they can actually do it in numbers. So make sure you're ready for both types of questions. So if they ask you what's 1 Avogadro's number of that, then you know. Now, this is 3 Avogadro's numbers up here in hydrogen. So you need to make sure that you know that that is 3 times Avogadro's number, 6.022 times 10 to the 23rd. So you're going to take 3 times that. So what would that be? That would be about 18, right? 0.066 times 10 to the 23rd, or 1.8 times 10 to the 24. So you need to be able to recognize that. Okay? So make sure you're looking for that. Again, down here at the bottom, 4 Avogadro's numbers would be, if we took this one down here, we'd go 4 times 6.022 times 10 to the 23rd. And 6 times 4, you've got 24.088 times 10 to the 23rd, which becomes 2.4088 times 10 to the 24th. So you can really quickly do that. So don't let them get you thrown off by saying, okay, that's, if I have 1 Avogadro's number of hydrogen, phosphoric acid, which H3PO4 is, how many Avogadro's numbers of oxygen do I have? You're just looking at the subscript and you're multiplying Avogadro's number by it. Okay, so if we want to find the percent of an element in a compound, we need to first add it up like we do on any others to find the formula mass. So we'd look up magnesium, and magnesium is 24.305. Sulfur, we have 1 of those, and that's 32.067. And oxygen, we have 4 of them at 15.999. So we're going to take and we're going to add those up. And there's a reason I do it like this. It just makes it nicer to find the percent. Okay, so this adds up to 120.368. Now to get the percent, remember that we're going to take and divide each of these by the total. So we're going to take this and divide it by 120.368 and then times it by, that's a times sign, 100 to get our answer for a percent. Do the same thing here and times it by 100 divided by 120.368 and times it by 100. Okay, when we report percent, report it to 2 after the decimal. So we're going to do that really quickly. So for magnesium, I get 20.19% of magnesium. For sulfur, I get 26.64%. And for oxygen, I get 53.17% for oxygen. Now hopefully this adds up to equal 100. And it does. I get 100%. So that's my double check to make sure that I did it right. If I've done my percent right, I should get within 0.01, depending on rounding. So I can find the percent of any element in a compound. Okay, that's all, folks. Make your 3x5 card. Remember, one side only for the test. Good luck. Study hard. If you didn't understand any of this or want some extra help, come on in. I'm there at 6:45 in the morning and there till at least 3:30 in the afternoon. See you in class.